Hi Year 12, so let's have a little look at your mechanics paper. So we'll start with the multiple choice. Okay, so question 1, you can see a lift, which is an elevator, is operated by an electric motor. It moves between the 10th floor and the 2nd floor, so you know it's going down, at a constant speed. That is absolutely crucial. One main energy transformation during this journey is... Okay, well, if you're told that you have constant speed, then a half mv squared, which is your kinetic energy, is also constant. Okay, so for a transformation, you have to have a change in the value of that type of energy. So we want to make sure that we don't have kinetic energy as one of the options in our transformation, because we're told that it moves at a constant speed. So the lift must have constant kinetic energy. So that literally gets rid of A, B and C, because we don't have a change in kinetic energy. Leaving us with D, we have electrical energy. There will be some heat loss to the surroundings, and obviously the electrical energy is the thing that's powering the elevator in the first place. So that leaves us with D. Okay, number 2 then. A ball is initially at rest. It's dropped in the air from a great height. It tells us that so that we know we have to factor air resistance in. Which of the following graphs best shows the variation with time t of the acceleration of the ball? Well, we know Marcus's favourite. Acceleration is force divided by mass. The mass of the ball is constant, so what we need to do to look at how the acceleration changes is look at how the force on the ball changes over time. So I'm just going to zoom out a little bit and have a think. At time 0, we know the ball is initially at rest, so it's not falling through any air at this point. And so the only force we have is the weight. Okay, so the resultant force is down and the acceleration is down, and the value of that acceleration will be g at this point. Excuse me. Now, as it begins to accelerate, it starts to bump into some of the air molecules, and at that point there's going to be a little bit of resistance up, and so at some time later the ball obviously continues to have its weight down, but due to the fact that it's now falling through air, there will be a little bit of air resistance. Okay, this means that we have a slightly lower resultant force than before. Okay, so we've got the weight minus r. So we know at this point that acceleration is now smaller than g. It's decreasing. Okay, at some point when the ball reaches terminal velocity, the weight down will be equal and opposite to the air resistance up, and the resultant force is 0. Now, if we have no force when these are balanced, then we also have no acceleration. So we know that because it's dropped from a great height, it's very likely to reach terminal velocity. So we're looking for a graph that acceleration tends towards 0. So we can get rid of A and B. And now we have to decide whether or not it's a linear graph or not. Excuse me, sorry, I should have cleared my throat before I started this. So we know that at all points in time there is a positive acceleration. Okay, so velocity is always increasing up until the point that terminal velocity is reached. But the rate at which the velocity increases is decreasing. Okay, as it accelerates and reaches a higher velocity, it means that it's going to hit more air molecules per second. And so proportionally, you've got more air resistance as it's accelerating. But as it accelerates at a lesser rate, so it doesn't speed up as much, it no longer linearly increases the amount of air molecules that it is going to hit, okay, because the rate of change of velocity is decreasing slightly. Okay, so we're looking for a non-linear graph, so that gives us C. Okay, question 3 then. We've got a constant force acting on a mass that is initially at rest. Which of the following graphs best show how the kinetic energy of the mass changes with the work done on the mass? Friction is negligible. So that tells us that there's no energy loss due to friction. And so that tells us then that if we have the object and a constant force is being applied to it and it's initially at rest, then there's going to be work done that's equal to Fs, okay, as it moves through a distance s. If there's no energy loss to friction, then all of that work is going to be converted to kinetic energy. Okay, so at any given point, the work will be the kinetic energy, and so if you're plotting kinetic energy and work, you're going to have a y equals x graph. Okay, so for any given point, the work done has been transferred to the kinetic energy of the object. Okay, question 4. This one wasn't done too well actually. I was a bit concerned about this. So let's have a little look. We know work done as an equation is Fs cos theta, okay, where F is the force, S is the displacement, which led a lot of you to choosing D, okay, but that is not the full equation. If it was W equals Fs, then you could have claimed D, but that's not the case. You need to consider cos theta. Okay, so let's have a look at a box. Okay, if a force is applied F and it moves through a distance S and they are parallel to each other, then cos theta is 1 and it disappears and it becomes work is Fs, leading us to this one. But what if instead we send the same box along the same journey by adding a force that is not parallel to it? We're still causing it to move horizontally, so S is still horizontal, but the force is no longer horizontal. So we need, okay, the product of the force and the distance moved in the direction of the force. Okay, that includes the cos theta section. So we need to have F and S parallel to each other, and that gets us B. Okay, number 5. A pump extracts water from a well of depth H at a constant rate of R kilograms per second. What is the power required to raise this? Okay, so if we imagine we're extracting through a height H, we know that the energy gained is going to be gravitational potential energy, which is given by mgh, okay, mass times gravity times height. We know that this has to happen over a certain amount of time. We raise the water through this height h, okay, and that's going to be T. We know that we are asked to find power. Okay, now power is the rate at which energy is transferred, so it's energy over time. Okay, so that's going to be mgh over T. Okay, change in gravitational potential energy per unit time. But we are told that the rate R is in kilograms per second. So to calculate R, we must have found that from taking the mass and dividing by the time. Okay, so hopefully you can see now that if I highlight m over T in my power equation, I can replace it with R. Okay, so I can say power is equal to RGH, and that gets me B. Okay, number 6. So I've got a ball thrown vertically upwards and it comes down again. Air resistance is negligible. Which of the following graphs shows how the gravitational potential energy varies with time t? So again, let's write mgh for how we calculate gravitational potential energy. Okay, m and g are constants, so I can say that potential energy is directly proportional to the height of the ball at any given point in time. Okay. If air resistance is negligible, all we have is acceleration due to gravity. Okay, so that means that if I imagine the ball on the way up, it will be accelerating at minus 9.81, and then when it comes back down sometime later, it will then be accelerating at 9.81 meters per second squared. So this is on the way up, this is on the way down. So I've not made that very clear with my diagram. But we now know then that it will have some original velocity that it's thrown with, and on the way up it's decelerating. Okay, so its velocity is decreasing, which means that per unit time it's going to travel less and less per second in terms of height gain, okay, because it's decelerating. And then on the way down, obviously it's accelerating, so the velocity is increasing, so per second it will have travelled further as time goes on. Okay, so we want to have a little look at this. So we can see that for equal time jumps, if I go across, you'll see the change in potential energy going across is getting smaller and smaller and smaller, because the height change as we continue to decelerate is going to get smaller and smaller and smaller, okay, because it's slowing down. So per amount of time across, it won't go as high up in that segment, and then we'll reach its highest point and it will start to accelerate again. So again, for the same time jumps, you'll see, I'm not drawing that very clearly, okay, that the height fallen through each subsequent second is going to increase, so that gives us D. Okay, number 7, a horizontal force F acts on a sphere. So here's our sphere, here's F. A horizontal resistive force, which means it acts in the opposite direction to the force because it's resisting, is equal to kV squared. Okay, where V is the speed of the sphere and K is a constant. What is the terminal velocity of the sphere? Okay, so this value is reached when the resultant force is 0. Okay, so when the resultant force is 0, we know that the sphere will be moving at a steady speed, known as terminal velocity. So at this point, we can say that kV squared must equal F, but opposite to. But the minus sign just tells us that it's opposite to, but in value they have to be the same size. Okay, and then you just rearrange for V. So you've got V squared is F over K, and then V is then the square root of that. Okay, and that gets us to D. Okay, this one was a little bit trickier. You had to do a bit of thinking here. So number 8, the graph shows how the position of an object varies with time in the interval from 0 to 3 seconds. At what point does the instantaneous speed, so the speed at that given moment in time, of the object equal its average speed over the interval? Okay, so the average speed of the object is going to be found from the total distance over the total time. Okay, so hopefully you can see as a general idea, I know you don't have a calculator in this paper, but it's a general idea. Our total distance is about 3.5 meters, and it does that in approximately 3 seconds. Okay, so that's approximately equal to about 1.2, 1.1, something like that, but it's approximately equal to 1. Okay, so that's your average speed in a ballpark. Instantaneous speed is found from the tangent of the gradient, because think about it, you've got position divided by time. Y over x, position over time, gives us the instantaneous speed. Okay, so you can hopefully see that I've marked on the tangents at points A, B, C and D. Now, the speed at A is quite clearly 0 because the gradient has a value of 0 at that point. Okay, if I grab my ruler, it might be more obvious to see. Remember that these axes have the same scales, so 1 to 1, 2 to 2. So if I do this, that's about a gradient of 1. Okay, that is very clearly too steep a gradient. If I come this side, it might be clearer. Okay, that is not a gradient of 1 on this graph. So D is not showing an instant velocity of approximately 1. A is obviously 0. B, again, that is not going through 1, 1, 2, 2. 2, 2's up here somewhere. Okay, that's not bad. Okay, you can see 1, 1, you can see 2, 2, 3, 3. That's the closest that you're going to get, so that gets you C. Number 9. A person is standing at rest on the ground and experiences a downward gravitational force W and an upward normal force from the ground N, coming from there, but just so that you can see it, which according to Newton's third law is the force that together with W forms a force pair. So we know that W is a weight. Okay, so therefore the force pair from Newton's third law also has to be a weight. Okay, now the force down, that is the weight of the person, is due to the ground. Okay, so we've got the weight of the person due to the ground is what we're given. Let me slide that over. So therefore all we have to do is say it's the same type of force, but it's on the other thing due to the first one. Okay, so it's the weight of the ground due to the person. Okay, so therefore it acts on the ground. We pick A. Last but not least on the multiple choice. A car takes 20 minutes to climb a hill at constant speed. Okay, so that means the kinetic energy is constant. That's really important. The mass of the car is 1,200 kilograms. So let's write these things down actually as we go. So we've got T is 20 minutes, but we know that time needs to be in seconds. So we've got 20 lots of 60 seconds is going to give us 1,200 seconds. The mass of the car M is 1,200 kilograms. And the car gains gravitational potential energy at a rate of 6 kilowatts. So rate of energy is power, so that's 6,000 watts. Don't forget to convert that. And G, they say, because it's for your multiple choice paper, they'll allow you to take it as 10. Okay, and it asks you to find the height of the hill. So energy is being supplied at a rate of 6,000 joules per second. Okay. As it climbs the hill, it doesn't gain any kinetic energy, so all energy, or work put in, is converted to gravitational potential energy, okay, which is obviously mgh. To find the total amount of work put in, we have to find the power multiplied by the time, because this is joules per second. For the number of seconds will give us the total amount of joules, and that gives us mgh. So we've got 6,000 watts multiplied by 1,200 seconds must equal 1,200 kilograms multiplied by 10 multiplied by the height. Okay, hopefully you can see that these cancel, and so therefore h is just equal to 6,000 over 10 gives us 600 meters, and that gives us answer C.